This video is going to be on question number 8 in your notes, something called heat exchange in aqueous solutions. Let me see if I can get this evened up a little bit. So there's often an energy or heat exchange between substances as a compound is dissolved in water or when a reaction occurs in aqueous solution. So like if you do like sodium hydroxide with hydrochloric acid, there's probably going to be some heat either absorbed or given off as those two aqueous solutions react. Okay, or just sometimes just dissolving something in water. So, for example, here, ammonium chloride as it dissolves in water. So if we do some ammonium chloride as a solid, if I dissolve that in some water, so it's just dissolving, so that means it's going to split apart into ammonium ions and some chlorine ions. So those are going to be aqueous. So really no chemical reaction there. There's typically an enthalpy change when this happens. Sorry. A little crooked here, it looks like. I don't know why. So the enthalpy change for that is right here, 14.7 kilojoules per mole. So what that means is for every mole of NH4Cl that dissolves, it's going to absorb 14.7 kilojoules of heat. What that means is if we put that in water, the water is going to get colder. It's taking heat from the water into the NH4Cl. So if you put that in a beaker of water, if we put some water in here, put in some NH4Cl, every mole of this compound is going to take 14.7 kilojoules of heat out of the water and out of the beaker. So we probably feel the beaker getting colder and the water getting colder. So even though it's endothermic, heat is being absorbed into this. When you put a thermometer in the solution would actually get colder, okay, as that happens. So it's exothermic for the water, endothermic for the substance it's dissolving here. All right, here's the first problem. In a coffee cup calorimeter, 50 milliliters of 0.1 molar AgNO3, and there's supposed to be a number there, and 50 milliliters, that's supposed to say 50 right there, not 0, sorry. There should be a 50. And 50 milliliters of 0.1 molar HCl are mixed to yield the following reaction. There's your net ionic equation. So we have equal moles of these, 0.05 liters and 0.1 molar would be 0.005 moles of Ag, and 0.005 moles of that. So they're both limiting reactants. They're both running out. Okay, both running out in that case. Two solutions were initially at 22.6 degrees Celsius. Final temperature is 23.4 degrees Celsius. Figure out the heat that accompanied this reaction in kilojoules per mole of AgCl form. So we want to know, eventually we want to know what is the enthalpy change of this in kilojoules per mole. Kilojoules per mole. Sorry, you probably can't see that very well. And notice that it says this total combined solution has a mass of 100 grams, and the specific heat is that. That is not just the water, that is the solution. Well, that is also the water, but in this case, it will usually give you specific heat of the total solution and the mass of the total solution. So we can do a little Q equals MC delta T initially. So our mass, 100 grams of our solution. Specific heat is 4.18, and our change in temperature would be 23.4 minus 22.6 would be 0.8 degrees. And remember that will be in joules. It's 334.4 joules. So that is if we think about that, the solution is getting hotter, okay? Solution getting hotter. That means that as this is dissolving, okay, as this reaction is happening, okay, solution's getting hotter, this reaction must be giving off some heat. Okay, so our delta H for this reaction has to be negative. This is the heat gained by the solution. So this many joules of heat were gained by the solution. That means that this many joules of heat were given off as this reaction happened, okay, because the solution is getting warmer. So That is positive for the solution. It'd be negative for the reaction itself. We want to know kilojoules per mole. So let's convert this into kilojoules. Convert into kilojoules. So that'd be 0.3344 kilojoules. We want to know per mole. Well, this is the number of kilojoules for 0.005 moles that are reacting. And remember, we're using 0.005 of that, 0.005 of that, and making 0.005 of that. So that is the number of kilojoules per 0.005 moles that are reacting. That'll give us our kilojoules per mole, which is going to be 66.9. per mole. Remember, this was the heat gained by the solution. That means the reaction is actually an exothermic reaction. The heat is going, this reaction happens, as those two things react, the silver nitrate and the hydrochloric acid, they're giving off heat to the solution. That's why the solution got warmer. So the reaction itself has this delta H. Another one. Pretty similar problem. So you got a coffee cup calendar with 125 grams of water in it, and they're adding in some 10.5 grams potassium bromide, and then the KBr is just dissolving. So the KBr, in this case, some KBr solid is just going into some water and dissolving. So making K plus ions plus Br negative ions. We want to know the enthalpy change for this in joules per gram and in kilojoules per mole. Joules per gram and kilojoules per mole. Notice that the water temperature goes from 24.2 down to 21.1. The water is getting colder, and we're putting it in 125 grams of water, and this weighs 10.5 grams. So water's getting colder. That means the heat must be going out of the water into this. So our enthalpy change for this is going to be positive. Heat is going out of the water, going into the KBr. So at the end, I know this is going to be a positive value. So let's do a little Q equals MC delta T. And our mass would need to be our total solution mass. So 125 plus the 10.5, so 135.5 grams. Specific heat of the solution is 4.18. A lot of times they'll make it to be like 4.2, but state is 4.18 here. And our change in temperature, 21.1 minus 24.2 would be 3.1 degrees Celsius is our change. And our joules there are 1,770 joules. Remember, that is the heat that is lost by the water, gained by the KBr. Okay, so we'll say it's a positive value for the KBr. And it wants to know joules per gram. Well, that is the number of joules per 10.5 grams of KBr that dissolve. So if I divide this by this, that would tell me my joules per gram. And that would be 168 joules per gram per gram of KBr. That's the number of joules per gram of KBr. So that's one answer I want. It also wants the answer in kilojoules per mole. So we can just take this and turn it into kilojoules per mole. So we know that there's 1,000 joules per kilojoule. Grams on bottom, we can go grams of KBr per mole of KBr. That gets to kilojoules per mole, and this is 119. So if we do that, I end up with 20.1 kilojoules per mole. Positive value. So for every gram of KBr that dissolves, there's 168 joules that's absorbed. For every mole of KBr that's dissolved, it absorbs 20.1 kilojoules. And again, it's absorbing that from the solution, from the water, making the water get colder. Here's one more example question. We got 11 grams of calcium chloride dissolved in 125 grams of water. Both substances 25 degrees Celsius. Calculate the final temperature of the solution, assuming no heat loss to the surroundings. Assuming the solution has a specific heat capacity of 4.18. So notice that calcium chloride dissolving is an exothermic process. It's giving off heat as it dissolves. That means that the water has to be going up in temperature. The solution has to go up in temperature. So our temperature should be higher than 25 degrees Celsius. It should be going up. So I know this is exothermic by the negative sign as this happens. So first thing we need to do is figure out how much heat would 11 grams give off. We know that every mole of calcium chloride gives off this much heat. Let's figure out how much heat 11 grams gives off. So let's do a little stoichiometry to start with. So we're going to go 11 grams of calcium chloride. And calcium chloride is 111 grams per mole. So that's 0.01 moles. 0.1 moles, excuse me. And then we know that every mole of calcium chloride that dissolves gives off 81.5 kilojoules of heat. So we get about how many kilojoules of heat are given off when 11 grams of calcium chloride dissolves. So now we want to know the change in temperature of the water. So we can figure out the change in temperature of the water by plugging that into make that our Q value. Remember, it needs to be in joules. So make that our Q. So we'll go below Q equals MC delta T. And we want to know, we'll put this number in here, so that'd be 8080 joules. I'm going to make that positive because I know that the solution is gaining that heat. The calcium chloride is giving off this heat. The heat's going into the solution. So that many joules equals, our mass needs to be our total mass. So 125 plus 11. It's 136. Specific heat of the solution. And I could do final minus 25, or I can just go delta T here and solve for delta T and know that I'm going to add it on to 25 degrees Celsius because I know the temperature is getting hotter. So multiply those, divide them over, and I get a change in temperature of, must be about 14.2 degrees Celsius. That is our change in temperature of our solution. Well, it was at 25 degrees Celsius. So add those on, and we end up with 39. So when we dissolve 11 grams of water, 11 grams of calcium chloride in 125 grams of water, solution starts at 25 degrees Celsius, it'll go up to 39.2. If we had more water, temperature wouldn't change as much. If we had more calcium chloride, temperature would change more. That's it.